myself Dr. Yogesh. After giving the idea about the construction of a bipolar transistor, now giving the idea about the configurations. As we know, the transistor is a three-terminal device. It is an emitter, base, and the collector. There are basically three possible ways to connect with the electronic circuit, with one terminal being common to both in and out. Here I want to share one thing. For any linear circuit, it is a required. Generally, it is a required two terminal is acting as an input terminal, two terminal as an output terminal. But transistor having only three terminals: emitter, base, and collector. So we have to make one terminal as a common terminal that will work for the input as well as output. So in this regard, each method of connection responding differently to its input signal within the circuit and its static characteristics of the transistor with the each circuit arrangement. So in this regard, we have to connect one time as one terminal as a common. Suppose we are taking the base as a common, so it is named as a common base configuration. If emitter is acting as a common terminal, then it is named as a common emitter configuration. It is named as a common collector configuration. If collector terminal is acting as a common terminal. So it is having some property. Common base configuration has a voltage gain but no current gain. Emitter configuration has both current and voltage gain. Common collector configuration has the current gain but no voltage gain. So we generally use the common emitter configuration because it has both current and voltage gain. It is reason behind it because for the amplification both gain are required. Generally is the current gain. So in this we have the current gain. So generally we are getting the we are using the common emitter configuration. So students begin with the first common base configuration. As name suggests, the base connection is common to both input signal and the output signal. The input signals are paired between the transistor base and the emitter terminal, while the corresponding output signal is taken from between the base and the collector terminal. Now just understand this circuit diagram. Here using the PNP transistor because arrow is the invert, so it is a PNP transistor. Now why it is so called the common base? Because now here you see we are applying the input VIN through a resistor in between the emitter and the base terminal, and we are taking the output just across the RL in between the collector to base terminal. So here we can see the base is common to both input as well as output. That's why it's so called common base configuration. Here one thing also remember, we have to make input side as a forward bias and output side as a reverse bias. Let's have a check. This is the NPNP transistor. So P terminal must be connected to the positive terminal of battery. Now here you can see P is connected to the positive terminal of battery. So it is the forward bias. Now check at the output side. It must be the reverse bias. Means N must be connected to the positive terminal or P must be connected to the negative terminal. So it is P and P. Now this is the P must be connected to the negative terminal of battery. Now here you can see P is connected to the negative terminal. So it is very clear this is acting as a forward bias and this is acting as a reverse bias. Why it is so needed? Because for transistor to operate in the active region for the faithful amplification, it is a mandatory condition. Input side must be acting as a forward bias and output side must be acting as a reverse bias. So it is the common base configuration. Let's have a look at the parameter. The parameter is a common base voltage gain, that is the gain voltage gain is nothing but output voltage divided by input voltage. So the ratio of the output voltage to the input voltage. So output voltage is V is equal to I into R. Output current is the collector current and RL is the load resistance. And input voltage is nothing but IE into RIM. I is the input current is the emitter current and RI is the input resistance. So this is the common base configuration voltage. Now let's another configuration is the common emitter configuration. In the common emitter or grounded emitter configuration, the input signal is applied between the base emitter and the output is taken from the collector in the emitter. Now here we look. Now in this we are using the NPN transistor because arrow is the outward. So now here you can see the E terminal, this is the base terminal and the collector terminal. Now let's check either it is working as a common emitter configuration or not. So here we can say the input supply is connected through a resistor in between the base to emitter and output is taken from the across RL in between the collector to emitter. So here we can see the emitter is common to both input as well as output. That's why it is called a common emitter configuration. Now let's have a look. that is acting as a forward bias, it must be acting as a reverse bias. So for actance is the NPN, so this is the P terminal, so P must be connected to the positive terminal of battery. So it is a connected to the positive terminal battery. So it is acting as a forward bias. Now here is the, it must be the reverse bias. Means N must be connected to the positive terminal battery. N is connected to the negative terminal battery. So it is acting as a reverse bias for the faithful amplification of the transistor. Now, there's a common emitter. The current gain of the common emitter transistor configuration is quite large at it is ratio of the IC upon IB, as we know. The transistor current gain is given the Greek symbol of beta, that is, here we know that. By combining the expression of both alpha beta, the mathematical relationship between these parameters and therefore current gain of transistor can be given as. We know that alpha is the IC upon IE for the alpha value, and beta is the IC upon IB, as we know. So IC is nothing but we can write is the beta IB, or we can say IC that can alpha I or beta I. So from this equation we can write alpha is equal to beta plus 1, or beta is equal to alpha upon 1 minus 1, because IE is must be equal to IC plus I. So this is a relationship between the alpha and the beta, and alpha beta is nothing but the current gain for the their construction that is common to the common base combination. Now, for the same, it is the input characteristics is what? The input characteristics describe the relationship between the input current or the base current. This input current that must be in the microampere, because base current is very low value, and the input voltage or the base emitter voltage, that is the VB. Here you can see the voltage. To determine the input characteristics, the output voltage VCE must be kept constant at 0 voltage, and the input voltage VB increased from 0 volts to different voltage level. For each voltage of input VB, the corresponding IB is recorded. Now here you can see the input voltage is increasing 0.2, 0.4, 0.6, 0.8 and 1, and according to that base current IB is having the 10, 20, 30 up to 80. For different value of VC, for VC is equal to 0, then it is giving the graph in this fashion. Means IB is increasing after 0.6 voltage, since it might be possible for the silicon transistor. For if increase the voltage VC, then VB value slightly increase, and then we are getting the graph in this fashion. For example, if we increase the voltage VC for, let's suppose, a 20 volt, then we will get the graph in this fashion. So this is the input characteristics of the common emitter configuration. So we can say the current is drawn between the input IB and the input voltage VB at the constant output voltage VC is equal to 0. Next, the output voltage VC increased from 0 voltage to certain voltage 10 volts, and the output voltage VC is kept constant at the 10 volt. While increasing the output voltage VC, the input voltage VB kept constant at 0 volt. After we kept the output voltage constant at 10 volt, the input voltage will be increased from the 0 to different voltage levels, as seen in the previous graph. For each voltage level of the input voltage VB, the corresponding voltage is recorded, as seen in the previous slide. This process is repeated for the higher fixed value of output voltage VC. Means we have to take the input VC, the VC value. First we have to take the graph between IB and VB for the VC is equal to 0, and then we have to increase for the 10 volt. Then we have to take the graph with IB and VB, and then we have to increase the voltage VC for the 20 volt. Then we have to take the graph with IB and VB. So in this fashion we are getting the graph just like a input characteristics IB and VB. Now, output characteristics for the common emitter. The output characteristics describe the relationship between the output voltage IC and the output voltage VC. Now here you can see the graph is divided into three regions. One is the active region, that is showing this graph. One is the cutoff region just below this active region, and this is graph showing the saturation. And this for the different value of IB, for example, 0 microampere, 20 microampere, 40 microampere. We are getting the different value of IB and the different value of VC. So this is the output characteristics of the common emitter configuration. So a curve is, we can say some description of this output characteristic. The curve is drawn for the output current IC and the output voltage VC and the constant input current I. When the base current or the input current is 0 microampere, the transistor operates in the cutoff region. In this region, the both junctions are the reverse bias. Next, the input current IB is increased from 0 microampere to 20 microampere by reducing the input voltage VB. The input current IB is kept constant at 20 microampere, as you see in the graph. After we kept the input current IB the constant at 20 microampere, the output voltage VC is increased from 0 volts to different voltage level. For each voltage level of output voltage, the corresponding output voltage IC is recorded, as is seen in the just previous graph. A curve is then drawn between the output IC and output voltage VCE input current for the input current IB 20 microampere. This region is called the active region of the transistor. Now third configuration is the common collector configuration. In the common collector or grounded collector configuration, the collector is connected to the ground through the supply. Thus, the collector terminal is common to both input and the output. This type of configuration commonly known as the voltage follower or the emitter follower circuit. Now let's look. In this, the collector is common to both input as well as output. That's why it's common collector configuration. The common collector current it is there is an AI that is IE upon IB. This is the I is the output current, IB is the input current. I we can write IC plus IB. So IC plus IB upon IB. So this is take the fraction of this. So IB upon IB 1 and IC upon IB. So AI is equal to IC upon IB plus 1. Now relationship between the DC current and the gain. We know that I is equal to IB plus IC, so we can write IC is equal to I minus IB, or we can write IB is equal to I minus IC. Alpha, we know that IC upon IE is equal to beta upon 1 minus beta, that relation between the alpha and the beta. Beta, we know that IC upon IB, that relation between beta and alpha is equal to alpha or 1 minus alpha. So we can write IB is equal to IC upon beta. IC upon beta we can write convert into the I upon 1 plus beta, that is IE 1 plus beta we can write 1 upon 1 plus beta we can write 1 minus alpha. So we can write IC is equal to beta IB, that is alpha IE. So IE can write IC upon alpha, or we can write IB is equal to 1 plus beta. So here we can say in this video we understood the concept of the configuration, that is the three type of configuration: common base, common emitter and common collector, and their input and output is for the common emitter, and generally we refer the common emitter configuration. Okay, so I hope you understood all the configuration. Thank you so much.